Okay, thank you, Oleg. Good afternoon, everybody. Okay, so I'm talking about the modeling I did on the 3D Bushveld complex. I'm mentioning my co-authors here because they were hugely helpful and gave me lots of guidance and supervision and assisted me. And it's important that I give them a shout out. I must just show this disclaimer that says that the information that is in this document is the council's property, and also it's not necessarily the views of the council that are expressed. So yeah. Okay, so where do we start when I talk about the Bushveld complex? I decided we'll start at the beginning because it's a very good place to start. So the first that I could see in a book about the Bushveld complex was in this book by Molengraaf, which was done, I think it was actually written in French first in 1902 and then translated in 1904. And he described it that he was talking about the granites that he saw, and he saw around the granites there were these norites and gabbros everywhere. And you could see them as these little hills that they formed. And then he describes the rocks as beautiful rocks. And then he mentions what rocks they are. But I want to change it a bit and say they are beautiful rocks that cause beautiful geophysical anomalies. So through time, the Bushveld complex, well, the Bushveld complex in our lifetime has obviously stayed the same, but our idea of what it looks like has changed. So I say the Bushveld complex is a shapeshifter. Molengraaf is a model that all of these I got from a memoir done by Hall in 1932, but he goes through these old models. And he showed that he saw the Bushveld as this big intrusion, like a light, he called it, and then later Daly also had a similar model. Pointer. But maybe a little different. He also had this feeder in the center. What was interesting is that at the deep level, he also had the crust sort of pressing down. Just to point that out. And then the tour in the same time had a model that showed this sort of basin continuous structural feature. And then in 1959, geophysics, the gravity data were published on the map, and Cousin said, but you have these two anomalies.
What?
Okay, somebody has the microphone on, so please just check. So he said he couldn't model these two anomalies with this type of a feature, and he modeled it as these two separate intrusions, which most of us probably would have done. But at the same time, well, this is later, but some people were still considering the Bushveld as sort of a cell-like intrusion, and not these lopolithic structures. And then more gravity and magnetics. Molyneux and Klinker did a magnetic model of the eastern lobe, and they modeled it as sort of a trough like that. And Hutton did gravity also in the eastern lobe, and it was also a trough shape. But then Duplessis and Clavak said, well, it can also be modeled as sheets. And then this was a very famous model by May and de Beer showing the Bushveld as dipping sheets. And I think this was, lots of people referred to this model in papers. It was widely used. It used resistivity data as well to help with the modeling. And then, of course, Grant and Sue thought, but came up with the idea that you had to have this isostatically depressed crust because due to the weight of the thick layer of the thick Rustenburg layered suite. And then when the SASI experiment, the Southern African seismic experiment was done, it turned out to be true that the crust underneath the Bushveld is depressed. So we're back to the sort of more continuous model because now it can't be modeled as two dipping sheets or two separate intrusions. And then also in the geological, with the geologists, it was often lots of people, although lots of people see it as separate lobes, there are those who saw it as a continuous body with the different layers or zones intruding at different stages or forming at different stages. And then this is sort of one of the latest things, and I felt I must show this because to me this is just quite an incredible image, incredible piece of work. If you can think you can go from there and go through all the structures and get back to what it might have looked like at the beginning. I mean, that's just amazing. So it also is one sort of single intrusion in this picture. So if we think about it, we started from here, where it's a single sort of body. Then we went here to there, and now we're back here. And all of this was supported by geophysical data. So as we got more data, our perception changed. Over time, we got more and more data. We also, there's very little bit of empty done. I know of 2 profiles going through, but unfortunately in the Bushveld complex, you have lots of DC trains, and that is just not, it doesn't work with empty. Because you can't process the data, it's so noisy. So basically what we're saying is that the more data you have, the understanding of bodies can change quite significantly. But is that all that we need? Is it more data? We also develop newer techniques and processing methods and modeling methods. So just a simple, I mean, I'm sure everybody, I know everybody knows this, but just an illustration that for a very simple body that's like a dike or something, doesn't matter if you're modeling 2.5D or 3D, you will get the same result. But as soon as you have a more complex geology, you can see now you start to see differences between the 2D and 3D, because the 3D modeling takes into account the change in the shape here, the effect of the model there on this profile. And if you make it even more complex, the differences become bigger and bigger. So this is why I then embarked on modeling the Bushveld in 3D. A big regional model like this hasn't been published of the whole Bushveld. So I took on the job. You might ask why I didn't do inversion, because I'm saying we must use newer and newer techniques. I've never been, I have nothing against inversion, and I've seen it used really amazingly well, but I wasn't used to doing inversion, to be honest, and I've wanted to do forward modeling. I've also seen very scary inversions. So maybe I don't know, maybe I'm a control freak or something, but I like the idea of doing a forward model. So in this shows the area where I modeled. So you will see that I didn't do really the northern lobe because Carol Finn, she did a nice model of this. So I just focused sort of on the main central part of the Bushveld complex. And this is the data I used. At the surface, obviously the elevation, then we had magnetics for the shallower stuff that shows mainly the upper zone magnetites, but also there's a bunch of remnantly magnetized or remnant anomalies, mostly related to the main zone, then the gravity. And then we also added the crustal thickness from the SAGA experiment data. I'll show just a bit more of it now. The constraints I had were the geological maps at the surface, petrophysical properties, which is crucial when you're doing, well, any kind of geophysical work. A few boreholes, but they're not too clear on this image, but I'll just show them. There's one, there's there, and they're all obviously around the periphery where the Bushveld is close or at the surface. So that is basically the boreholes, the deeper boreholes that we had to work with. And then there were a few seismic lines. This was done in the then geological survey of those two, and this is a JCI line that Jeff Campbell did and published. So the software I'm using is Pygmy. Pygmy is in-house developed at the Council by Patrick. It stands for Python, Geoscience, Modeling and Interpretation. Started off as just a 3D modeling of magnetic and gravity data, but it has grown enormously since then. You can do all kinds of other things with it. It uses voxels, basically, or cuboids, whatever you want to call it. So the model is made up of these little boxes. And since I had a very regional model and regional data, and I did want to continue to complete this in my lifetime, my voxels or cuboids were quite big, especially in the horizontal direction, 1.5 by 1.5 kilometers and 200 meters thick, because I needed a better resolution with depth. So it was, there's quite a lot of cuboids in it. And then, of course, you do need patience and perseverance and blood, sweat, and tears. Okay, so if we now look at the first data, because it's such a big feature that we're modeling, we know you have to include data that goes down deep, or deep data, I don't know how to say it right, but and also we knew now from the work that Sue and Grant did and from the SAGA work that there were definitely changes in the MOA or the crust MOA intersection where interface that has an effect on the gravity data. And when the data became available, people started to work on it, and lots of people came up with different models. So these are the 5 I looked at. So they used similarities but slightly different techniques. Maybe this one is quite a different method, shear wave velocities, but they also show clearly that under the Bushveld, the west, especially here in the west and the north, the crust is definitely thicker. Then some of them also show a bit here to the east, but these data here are not good quality. I think we needed more stations maybe, and there's also the escarpment. So these were problematic because you can see there's different models for it. So since I don't know which one is really correct, I decided to take the average of these 5 models, and it basically took the features and it shows the main feature there and then a little bit of the other features. And this is what I used as the crust base of the crust. In the models that I will show, you won't see the crust. What I did was to calculate the gravity response for a model that extends further around the Bushveld area, and that gravity, the gravity values that I calculated, I added as the regional. So it's included in the model, but I'm not going to show it as part of the profiles. So just overview, these are just sort of images to see I did really do 3D modeling. And these are all the lithologies, and then this is just the Bushveld, and then just the Rustenburg-Lade suite modeled as a connected sort of cell type or sheet or intrusion, connected body, let's put it like that. This is the physical properties that I used. A lot of the magnetic information is from Sean Letz's thesis, and then obviously our petrophysical laboratory has a lot of data. And I also used Anglo-Platinum was kind enough in the beginning of the project to give me some wireline logging data. And I went through that data, and combining all of this, I came up with densities and susceptibilities and things that I used for the modeling. So if we look at the results, they sort of, it's like the Bushveld is both simple and complex in a way. In the west, it is the thickness is quite consistent. Obviously, along the edges, it's a bit thicker. We have the Crocodile River fragment, but otherwise, it's really just a sort of a solid or same thickness. And also the depth is pretty consistent. Depth to the top of the Rustenburg-Lade suite. But if you look at the east, there's a different story. Sorry if you can hear my dog crying. She wants me to play with her. So there's interruptions, areas where in my model, there's not really bush or Rustenburg-Lade suite present there. You've got all these diapirs and domes and things in the eastern lobe, which makes it a lot more complex. So we will look at these now along these profiles. I extracted some profiles just for easier discussion, and I'll just go through them systematically. So we'll first just look at the western bit. So I'm going to look first at this profile here. See, and I've sort of discovered the eastern bit so that we focus on the west. So here is the Crocodile River. It's called a fragment. And then basically the Bushveld comes down, the seismic suite, and then just levels out. And in the middle here is that sort of gravity high, and it can be modeled with sort of an anticline. Sue also had that in her model. And on this eye, you've got lots of just like pyroxenite intrusions and things. These pyroxenite intrusions cause very nice remnant magnetic anomalies up there. And the earline scroll complex is there. And then if we look at this model from south to north, again, it is, you've got the Crocodile River fragment, but otherwise, you know, there is a bit of a sort of an anticline there. I think that long ago, few far off and then also modeled something like that. And then if we look at this, it's very simple. So it's just a layered sort of body, basically a constant thickness. Now along this line was chosen, this one, because to show as because there's seismic data along there. It's Terry interpreted, I think, for his MSc. So here I've put my model extracted along that profile on here, and you see there are some problems with the comparison. I know that in the paper they mentioned that this area, the signal quality was quite bad. So it can be there where our biggest differences are. It might be just due to problems with the data. It can be also that they used a constant velocity to determine the thicknesses of 6 kilometers a second. And it might be that, well, I think the velocities will change through the different units. So I'm not trying to shoot down the model. I'm just saying there are discrepancies. But obviously one of the things can be that my model is just not right in this area. But that is that's how I had to model it to fit the gravity and the magnetics. So that is the western lobe. Now if we move to the eastern lobe, it's much more complex. We've got this gravity low here. This is the lowest gravity values in the Bushveld complex, in this part of the Bushveld complex, is in this area and here. And obviously you can model it in many different ways, and I chose 2 ways. One was to make the granites and things that are in here thick, because they are not so dense. And the other is to get rid of some of the dense Rustenburg layered material here. This whole area is full of domes and diapirism. And the whole Bushveld complex actually, I mean, if you look all around it, you've got these granite domes of the Archean. There's the Makopa and there's the Joburg dome. You've got granites on this side. And we also know from, I think Button, he showed a profile here in the Transvaal showing the floor to be very uneven. So it is conceivable that there can be like more updoming in this area and somehow also related to all these diapirism and things here. So if we look at the model, these are the 2 models I did. In the one, I had this sort of up-down basement. In this model, the Transvaal is over the basement, but then the Rustenburg layered suite doesn't go over the Transvaal. There's the gap, and then you have the granites. Of course, this is just a way to model it by varying the densities, the thicknesses of the various layers. You can, come up with quite a few different models. Then you have the Denelton dome. In the other model, I just decided to make the granite very thick. So that also accounts for that negative. We just go from south to north now. So if we look at this profile, it's that one. So you can see this negative here is actually this little negative here. And then we go into the main one. And here, this is where the other profile, the top profile goes through. So you can see there's Transvaal. And in places I even don't have the transvaal, I just have granite, Archean granite at the base. If we look at the other model in this along this profile, I had to make it quite thick, the granites, to fit the gravity low. And it goes through the Rustenburg layered suite, which is interesting in itself. And then just this profile here, going now through the Denelton dome, which I modeled here, as you can clearly see, as a diaper. I had to do it like that there has to be dense material. It's quite a complex thing to model, especially also in a regional thing, but there has to be dense material around this Denelton dome in order to fit these anomalies there. Otherwise, it's just sort of undulating almost in this model. Now, if we go to the southeastern lobe, is, in my opinion, well, I don't think it's just my opinion, but it is part of the whole eastern lobe. It continues here, and my feeling is in my model, it also continues here. There is the Dwarsfontein complex, which is also a layered intrusion. It's been seen at some point, was seen as a satellite of the Bushveld. Consists of upper zone and main zone. And I've seen different opinions about whether there's lower zone or critical zone, but there's definitely Bushveld type rocks there. So I modeled it as part of the Bushveld. There's some borals here that was done in 1978, and they encountered upper zone and lower zone here on this big anomaly. But if it's all part of the same complex and we have main zone in this area, then at some point it has to appear moving from south to north. So in my model, I have the main zone coming in round about here. Of course, again, it's quite thin here, but of course, playing with different thicknesses and changing thicknesses will change the values of the thicknesses and so on. But in the end, it's just more of a concept to think, but the main zone must start here somewhere. So this now shows this profile here. So we're going over the Johannesburg dome, and then here is the Dwarsfontein complex, which you can sort of see there. And then I'm just going to show you another profile there. Okay, we saw it earlier, but just to show you the yeah, that is the Dwarsfontein complex. Oh, I think I swapped these lines around. This profile CE. Okay. So there you can see the Dwarsfontein complex. I had to make I combined the lower and critical zone because you can't really distinguish between them on the gravity or on the magnetics on this regional scale. But it had to be quite thick in order to fit that anomaly. Then also, if we're coming back to my story of the main zone must be present somewhere, if we believe this reconstruction, obviously the main zone would have been in here somewhere, and then as it shifted around, it will be somewhere in here. Then if we look at the northern lobe, I didn't really do, as I said, a major thing on the northern lobe. Where I did cross over it, it's just a really horizontally layered body, quite thick. And I inferred some faults, also not just from the modeling, but also looking at the magnetic and gravity data. There's definitely a lot of faulting there. But the work that shows the best geophysical modeling of the northern lobe was done by Carol. When she did these models, it's inversion. She's very good with that. And so this shows the thickness of the Rustenburg layered suite, about 7 kilometers thick places. This shows the elevation. So this is where it's deepest, and this is where it's shallowest. So it's the elevation of the top surface. Then there's also a seismic line there. Once again, I selected this profile to coincide with the seismic line. So this was it was a conference in the third SAGA conference in Cape Town where Terry presented this. And I again show my model on top of it. But again, there's not really good correspondence. I have more complex modeling here in this area with some more updoming. But there's also another model of this. Fiona Sargent did a PhD on the Bushveld and lots of seismic lines. I think she got from mines and so on. But this was one of the lines she interpreted. And there's a much better correlation between my model and their interpretation. And also just to point out that Bushveld is still present here as we go further west. Okay, so now you've also seen that a lot of the I've modeled both the Crocodile River and the Denelton. They've been called, let me say, they've been called fragments, like and domes and things. The Crocodile River I've seen being called a dome and I've seen being called a diaper, but mostly it's known as the fragment. And the same with the Denelton. I've mostly seen it called the Denelton dome and the marble fragment. But we know that diapirism was very active or present during the inclusion of the Bushveld complex, especially there in the east where you have these Transvaal outcrops. And Brendan Clark and Mike Watkins and them, they did some nice work on the, and also Roger Schoon on the fossorial Zykloof dome, showing that they can be modeled as diapers. And it's important because the diapers brought up some of the deeper Rustenburg layered suite closer to the surface. So I also modeled the Crocodile River. I found that you really need to have, it works really well, let me say it like that, to model it as a diaper, but it needs a bit more work. This was very regional, but in my opinion, it might also have been a diaper. The carbonates maybe, I'm afraid that they can be viscous even at room temperature sometimes. So I don't know if that's true, but understanding the mechanics of that and the geological, the geochemistry, I haven't done. So I need to spend time on that. And then if we go to the east, the Denelton and Marble, the Denelton definitely I can model as a diaper. So I sort of made this rough, sort of very simple picture of maybe how it developed, that you had pre-existing basement high in the in the Archean basement, and the Bushveld intruded, and due to the heat and the pressure, then things became more viscous. I know granite depends on the granite when it will become, and the amount of water in it when it will become more viscous, but say it became viscous. And you had this diaper forming, and even here we only had the Transvaal moving up. And then at some point maybe this got disconnected. You have this little marble fragment there, and then you have the dome. Oh, this is just some of my thoughts. That needs obviously more work, but it's interesting to think of that. Okay, and then the last thing I want to show is this, the feeders. We modeled basically 3 feeders for the Rustenburg layered suite. I'm looking here from the south, sort of below the model. So southern lobe and Malopo anomaly there, and then there's another feeder. And then maybe possibly one for the granites in the eastern lobe. If we look first just at the granites, this is the thickness of the granites that are in my model. Now here, obviously, it's the thickest. And then if we go look at this profile across here, it's this one. So it looks a lot like a feeder in this model. Obviously, the deeper you go, the less sensitive the model is to changes. So it can be deeper and it can be shallower. But there is a sort of a depth with this density that I chose for the granite that you sort of want, it sort of doesn't change much more. So, and this is then just the model you saw earlier as well. Here it also looks like a feeder. So if if this negative is caused by the granites, I mean, it possibly maybe there is a feeder there. Then if we go to the feeders for the Rustenburg Lake Suite, in 1976, Maurits van der Merwe, who I believe is a dentist actually, but he was also a geologist, I think, and he modeled gravity data over the northern lobe. So that's the northern lobe, visible in NORA. You see the gravity data, and here I just show the data across this big anomaly here. And he modeled it sort of as a trough thing, but he calls this a type of a feeder where it's the deepest. It's going down to say 10 kilometers. His model just shows the Bushveld to basically go from there to there, whereas our model show it to go up to here. So, but in any case, he already modeled it as a feeder. And if you look, it's that anomaly, it's huge, it's 110 milligauss, and there's really only one way to model it with densities that make sense. So if you just give it a very high density that can be attributed to, say, lower zone rocks, you have to go down quite deep to even fit that anomaly. So this is Carol's model. She had it, I think, sort of 12 kilometers thick. And also mine is also there. There's no other way to model this. So this definitely, I think we can safely say, is a feeder, and it's here at the Diapirism matches in lineament. And there's lots of structures and things here. And we know that this lineament is a very, very big feature, crustal white feature. I mean, a crustal feature that goes down deep probably. And those types of features are very good for bringing up the fluids and stuff from deep. So it's a good candidate. And then when you have intersections of different lineaments, then it's even better. So now if we look, the second possible feeder is here along the Diapirism matches in lineament. This part of it is the geological thrust, and that there's a paper that I'm sure everybody's read by Good and De Wet, where they did a whole study on the Diapirism matches in lineament, and they show that, or they said they dated it and said that it could have been active during Bushveld times. Well, there's a gravity high under magnetic anomaly along here. Of course, there's also mapped penge formation, which is very magnetic. So I tried to model it just with a penge, but you can't really model that anomaly just with Transvaal rocks. You need something quite dense there. So then I put some dense material going deep, conceivably like next to the thrust, although here it's very vertical, but not necessarily doesn't have to be that vertical. But if I put dense material in there, then I can get the fit. And then at the top, there is some Bushveld, some banded iron formation to model the magnetics. And then it also continues further along here. And Carol also in her model, she also had dense material along the Diapirism matches in lineament. So it's possible that it served as a feeder for the Bushveld complex. And then some of the material got caught up in there, and they are now causing this gravity anomalies. And that is, I modeled it all along this geological thrust part of the Diapirism matches in lineament. So now we have, well, these two might be linked, but we have those two feeders. This also ties in nicely with some of the models out there, or the geological ideas, like this one by Pierre, showing the Diapirism matches in lineament as a major feeder. And then also Brendan Clark, he also had it in his work, that the Diapirism matches in a sort of an important feeder. But then if we go to the south, this anomaly here, it's quite big. Remember, this is under a kilometer or so of Peru and so sediments. And I had to also do the same here in order to fit the anomaly. I had to make a dense body that goes down quite deep. This might be a bit excessive, but because the only way I could really model it is to make it also a feeder-like structure. And what is interesting is that you have the sugar bush fault here. There's not too much written about it that I could find, but I did see that it was, I think, active in Wits times and maybe active again in Transvaal times. So I'm not sure if it was active during the intrusion of the Bushveld complex, but I don't know, conceivably they might be linked here. I'm not sure. But in any case, my feeling is the way we can model this is also as a feeder. So that is then, you can see it on the model here. So these are the 3 feeders for the Rustenburg layered suite in this model. Okay, so that's basically just a summary of the main features of the Bushveld that from the modeling. I can't go into too much detail. I mean, it was a lot of work, but so we're back to where we started. More data we have, we can try new things. The question is, what is next? Where are we going? Are we staying with this? Or do we need more information? Obviously, if we get more data, not just more gravity or magnetics, but other types of data that can tell us more different things about the Bushveld, it can help us to really improve our understanding of it. And here I'm just thinking of how nice it would be if we had like a deep seismic line across the Bushveld, but that is just a hope for maybe somewhere in the future. I don't know. But this is my story. Thank you.